โอเคค่ะ เสียงเข้าไหมไม่รู้ ฝากเช็ค ใครฝากเช็คใน Can you test whether or not my sorry Can you say it again I can't hear you Okay if those of you in Zoom if you can hear me if you cannot hear me let me know all right you can just text whether or not you can hear me from Zoom. All right, and welcome everyone once again, and welcome in international students, exchange students. Also, I believe most of you are from France, right? Ah, bonjour. It's the only thing I can say. But I love France. I just went there last year, so yeah, it was fun. Anyway, so last week, for those of you who would like to review the materials, or the recordings of the class, you can use the link, the Zoom link from my course bill, as I mentioned earlier. And now, from last time, we stopped at this point where we finished when we talked about OLTP and OLAP, and then we are going to continue about SQL or SQL. We already mentioned about SQL a little bit, but then we'll talk about it a little more, like where it came from, the root of SQL. So basically, SQL came in and is able to operate because of these background in set theory. Professor Cott, who actually started the SQL and also the relational database, came by doing so by getting or using the set theory and also relational algebra plus tuple relational calculus in order to offer how we could access the database in the manner of being a relational, where data are related within the database, all right? So the relational algebra uses the set union. You probably learned it from like high school before, but you probably all forgot about it. But it's like basically set union, different Cartesian product, or set. These are the I would say theories and practices from the base from set theory. But now he also Professor Cott said that aside from set theory, we also need extra commands to be able to use the relational model effectively. So he adds additional constraints to these operations. All right. Oops, sorry. Now, so basically it was originally based on relational algebra and tuple relational calculus, and it was one of the first commercial languages to use, right? When I say that it was the first commercial languages to use in relational database, I mean that at that time when he produced the language SQL itself, there was no SQL language before, right? But then afterward, many of the relational database products have been using SQL, but with different version, with some varieties. But finally, at the end, it becomes standard. So at the moment, if you are using or you are writing an SQL code, most of the time you'll be able to use the same SQL code with different RDBMS products as well. So on the right here, you will see the example of relational algebra commands and also the relational calculus commands. For example, the first line here says that we use this small sigma here. So say select from table called employee where sex equals F or female, and then keep everything in a relation called female ems. This is just the example of how the relational algebra command is used. ค่ะได้ละตอนแรกมันไม่ได้แต่มันหยุดหลายทีก็คืออย่างนี้ไอ้สิ่งที่หยุดคืออันนี้กล่องเนี้ยที่เปลี่ยนแล้วเอาเมื่อกี้ไม่ได้เปลี่ยนแต่ว่าเอาเข้าเอาออกเสียงใหม่แต่ว่าเดี๋ยวมันก็เป็นอีกเรื่อยๆค่ะ And below, you will see the example of relational calculus. So basically, when you use relational calculus or algebra, they are the same. You can do it, you can use one or the other. But the thing is that when you use relational algebra, the operations will be performing step by step. But when they use relational calculus, it's the whole thing. You can issue just one command. So when the objective is fulfilled, then the results from the table will appear, right? ขอบคุณค่ะค่ะเมื่อกี้โทรไปตอนแรกไม่มีใครรับสายเลยอืมไม่ที่ ISE อ่ะเบอร์กลางยังไม่มีเลยอ๋อขอบคุณอุ้ยตายแล้ว Okay, I broke the microphone. Anyway, so sorry about the interruption because the machine wasn't working well. All right. So let me ask you a little bit. Who likes algebra? Who prefer algebra than calculus? Me, who likes algebra more than calculus? Okay. And who likes calculus more than algebra? Okay, some of you. Who doesn't like anything? So no calculus, no algebra, right? We just want to go through life without them. But you can't, right? You have to use one or the other. So basically within our class, we'll focus on relational algebra so that you understand the step that the database is working, right? Now, we talked about SQL, then we are at the interest of NoSQL. So I'll skip this because it takes time, okay? So NoSQL actually stands for not only SQL or non-SQL. It doesn't mean like, no, I don't want to touch SQL at all. And it's not like something like that. However, the NoSQL is just another type of another class of database, which actually would like to, how do I say, would like to tackle a problem where the SQL cannot do. For example, whenever we have like very large volumes of data, right? Very large volume of data. Basically, when you have big data, you will come up or you will see the data without structures. For example, if you imagine getting into the internet as a whole, so you get on one website, you see a lot of information, but most of the time, the information doesn't have any rigid properties or any structures that you can work with in the database automatically. So basically, this is not good or not appropriate to work with the SQL databases. This is where NoSQL comes in. It tackles a problem when you have large volumes of data without using, can't use a fixed data schema, table schema. So when you do this, when you have NoSQL, usually it is very much scalable because you can scale the database at any time, and it becomes very flexible because you don't have the rigid structure. So it is suitable for distributed system. However, it doesn't mean that, well, so this is good. We just drop the NoSQL altogether. I'm sorry, just drop the SQL altogether. But no, because most of the time when you have this, you have to trade off with something. So when you trade off NoSQL and SQL, usually when the SQL, you understand the meaning of the data automatically or intuitively. But with NoSQL, you have to gain the understanding afterward, after you have a lot of data. And also you kind of trade off the security purposes of the database. So of course, when you gain some of the advantages, you probably lose some of the advantages as well. So it's always a trade-off between NoSQL and SQL databases. Uh, but I said, yeah, of course, if you trade it with NoSQL, it's scalable, it's flexible, it's high performance. So basically come back to like, not only because you have large volume, but also because when you have a lot of users at the same time and you want to reduce latency, you want to reduce that delays, NoSQL will be able to work with large data without structure very, very fast. So large volume, fast, and scalable is the advantages of NoSQL. Now, I have this table here that compares SQL databases and NoSQL databases. When I say SQL databases, of course, the base of the model is always relational model, all right? And we saw it from last week that the relational model is still much more popular. Well, I wouldn't say much more, but it is like among the top popular databases in the world today. So that is the reason why we still need to work with SQL database and also NoSQL. And most of the times in the world right now, most of the large companies will be using fixed database schemas or fixed database schools, like NoSQL and SQL together. But they will decide which operations or which transactions are more suitable with what kind of databases, and that's the properties that you should understand in order to select the database correctly. So now with the SQL and NoSQL here, the data model is relational versus non-relational. For relational, you only have one thing. You have the table. Within the table, you have rows and columns. So you could imagine something like Google Sheet or Excel. So that's the format that the table in database looks like. Well, for NoSQL, the database doesn't look like table anymore. So basically, there are like document types, key value types, column or graph, which you will see more details in the next slide. For the schema, of course, I already mentioned about this. The schema for database in SQL are pretty much very fixed. You know exactly like this is the student ID, this is name, this is last name, this is date of birth, so and so. So it's fixed. While for NoSQL, it's not fixed or schemaless. For example, you probably have first name and last name, but you don't have prefix. Or you have the address, but you probably don't have the zip code, for example. So you can't really have like fixed structure there. For the data type, within SQL, we call structured data. And of course, for NoSQL, it's semi-structured or unstructured at all. For query language, it becomes standard that SQL is used for any relational database, but for the NoSQL, it's usually the specific APIs for each type of NoSQL or query languages of its own. It doesn't become standard, or at least it doesn't have standard right now. For scalability, if you have a very large database, for example, if you imagine you have a university registration database, right? And now you have more students, or you want to keep more data, what happened is that you need to scale the engines, right? You need to scale the database. The only thing you can do when you have SQL database or SQL database is that you need to scale up vertically, meaning that you have to buy more machines, right? More database. But if you use NoSQL, you scale horizontally, meaning that you are in cloud, and then you can just scale the cloud out in order to handle or in order to process higher volume of information. All right. So it is much more economical if you use horizontal scaling with NoSQL, if and only if your database is volatile. I mean, some of the times you have a lot of users, a lot of information, and some of the time you probably have very small number of users, then using NoSQL will be economical in that sense. Now, for the consistency model and the transactions will come together. I mean, the consistency model, last time we talked about ACID property, the atomicity, consistency, isolation, and durability, which is the acronym for ACID. We talk about how strong the database or that particular database management system is good at. But for the NoSQL database, it doesn't have anything to do with ACID pretty much. So basically it is, you have to tune the consistency of the database yourself. What it means is that if you use SQL database to have the atomicity, the durability, the consistency, or those properties will be done or will be managed by the DBMS. But for NoSQL, you have to write extra code in order to take care of those properties within the database. And then when you have transactions that you run in each type of database, for the SQL databases, of course, the ACID property or ACID support will be done automatically by the DBMS, while the NoSQL doesn't have that. So you have to write it at the application level. Now, so if you are using the database, you should have to focus on the performance too. So if you have a lot of complex queries and you need to join a lot of tables, then SQL database would be something that is right for that kind of operations. But if you have like a lot of data if you imagine like JSON string, then it is more suitable with NoSQL when you don't have to join the table to understand the meaning, all right, to obtain the relationship. Because, if you use the relationship, it's better to use SQL or relational database anyway. But if you don't, then NoSQL would be the answer for you. Typical use case for the SQL database would be like financial systems, ERP reporting, or university registration, so and so. When you see that the information have particular structure, like you have name, you have ID, you have birth date, you have course information, so and so. But if the information are so sparse, then you probably look at the NoSQL database. So the typical use case for NoSQL would be like big data, real-time applications, IoT, or social media, where you probably need to see the node and link between them, but you don't need the relationship between all the information. So example of the products in the SQL that we are familiar with might be like MySQL, Postgres, Oracle, or I like to use MariaDB. Have anyone heard of MariaDB before? Anyone? Yep. Have you used it? I kind of like it though. And right now, what I use most is Maria and Postgres SQL. I think Postgres is really an up and coming. Before that, I've been using MySQL for a very, very long time. And even before that, I've been using Oracle. So at the moment, if you start using the first RDBMS, I would probably suggest PostSQL because Postgres SQL because of its function and also because of its AI ability as well. Okay. For NoSQL, of course, you will be using Mongo in this class, but there are other NoSQL that you should be aware of, like Cassandra, Redis, so and so. But we already talked about CAP theorem, and you probably remember that within CAP theorem, each of these products here will match with different properties that you require when you design the database, right? Now, so we know that we have so many NoSQL. So these are some of the NoSQL type. Of course, I'm not saying that these are everything, because there are more, but these are one of the popular ones. Let's start with the key value store. So the way that the NoSQL called key value store operates, that it takes a look at the data such that the relationship of the data is key and values, and that's it. So they create each pair of the value of the key value pairs, and those are the relationships, and that's it. So when you look at the key and value store, it should be something very simple, and you need something very fast to access. So simple information that link just key and value. For example, you have name and then you have value. You have last name and you have value. When you have key without value, it it would not appear in the database. You only have the key and value associated within the database. So if you have nothing with that particular value, then it doesn't matter, right? For example, let me give you some of the examples. If you look at the internet, right? Probably let's take a look at the example when you read the news. When you read the news, you probably see name, last name, you see the date, you see uh the content there, but you probably see a lot of name, but it doesn't have any structure. Sometimes you see just name and no last name. So what key and value does is that it says name and then it put the value of the name associated to it. When it doesn't have the last name, it doesn't care. But if it has both name and last name, you have name and value, last name and value, like that. All right. So just key the value that the data actually appears. The example products like Redis and Amazon DynamoDB is very good products for key value stores. And the typical use case are like, like if you want to maintain the sessions on the systems that you are working on, or you want to do catching, then key and value are perfect choice for you. For the document store, which is the model of the MongoDB or CouchDB, you probably have heard of course, because it is the document type. So the way that it keeps the information, it treats the data as documents. So for each document would be in the format of like JSON or BSON. So it is a semi-structure, and then for the next document will be nested with the document before. So all the document will be nested according to whatever you want to define within your NoSQL or MongoDB database. And then so the typical use case for the document store would be like content management, profiles or catalogs, things like that, right? For column and family store, uh it is very good for large scale data, sparse data where information doesn't really relate much. So for the column family store, it has you probably look at the data like you have many columns, and then instead of having every row related, it doesn't matter. You just say like these group of columns are grouped into families, but these is grouped into another family. So it becomes more flexible that way, right? So that's how the column family store works. And the product is Apache Cassandra or HBase. And it is good for time series, analytics, or logs. And actually, you'll be surprised because there is another time series database down here as well. All right, so let me skip to time series database first. So for whichever data that you mostly working with the stamped time stamped record, you could start looking at the time series database because it is very good at looking at the data and manage it according to time, right? So if time is an essence, then time series database would be good. So basically, like you have to monitor the usage of your system from one time to the other. Then if it's according to time, then you use this time series database. Like IoT, telemetry is good. And the product that I put as examples here are InfluxDB or TimescaleDB. So it's good for metrics, sensor data. And then finally, the graph database here. Of course, for graph database, you probably work in with the data, with the nature of nodes and edges. So if you have data that connected to each other in that sense, like the social networks data, then you can use graph database. So Neo4j or Amazon Neptune are very famous graph databases. NoSQL. So for on this slide, they are all NoSQL examples, right? Now, if we look at the comparisons between relational database or SQL database with document type, the key value store, the search engine, and vector DB, I added the vector DB at the end here because it is another up and coming. I already mentioned it last time, but I wanted to say it again because with vector DB, the difference from vector DB from the rest is that usually when you want to obtain the data from the database, you will find the match of the data, right? For example, I said, yeah, I want to obtain every student who takes this class and receives an A, for example. So what happened is that in the database, it try to find exact match, of the grade A, and then course code is this number, find exact match. But vector DB doesn't do that. Vector DB has another characteristics or another, how do I say, advantages is that in that vector database would try to find similar meaning. So it works on semantic rather than the exact match. So if you want to expand the search, aside from finding exact match, then vector DB is really, really good. So you could take a look at vector DB because I believe, and also you see the evidence from Gartner report last week that I talked about. Gartner report also mentioned about vector DB. That is a technology that you should look at. So if you are going to work as an intern by the end of the semester, then if you're lucky enough, maybe the company may be using vector DB, but you can practice using vector DB also. So now when I said the advantages of vector DB is to find or to search for different information with meaning or semantic notation, then the rest of the database models here actually search for exact match. And that idea is you probably see search engine, right? At the beginning, search engine or, so far the search engine, if you talk about search engine without AI at all, then search engine will just try to look at the exact information that you wanted to find and then retrieve the information closest to those exact match. And then they rank the similarities and then, give you the results. And the rest also work in the same manner. But primary data for relational database are tables, like I mentioned before. The document DB would be JSON, key value would be key and value. Search engine would be text and inverted index. And then vector DB would keep information in high dimensional vectors. So you could probably imagine that if you want to keep the data in the dimensional types, then it would take a lot more spaces. And perhaps it would take a lot more performances. I mean, not performances, a lot more energies or powers in order to work on the vector database. For schema, relational, of course, would be fixed, but for document, key value, and search engine, they are pretty much flexible or no structure at all. And for vector would be vector plus metadata to understand the meaning of each of the vector. For the query style, of course, relational would be exact match. The document would be document indexes. Oh, sorry, would be field-based queries. The key value would be key lookup, and search engine would be keyword relevance, while the vector would be on similarity or nearest neighbors. The index type, relational database would use B3 or hash pretty much. Actually, there are more, but mainly would be B3 and hash. But for document DB would be document indexes. Key value would use hash table, and search engine would use inverted index, while the vector would be ANN. It's neural network. Actually, it's like AI pretty much, right? Similarity search for relational DB, it's not native. So the only thing that is working for the similarity search is vector DB here. Okay. For transactions or asset property, of course, I mentioned this many times. So relational database is designed and is the one who proposed the idea of asset property. So the rest doesn't really have the asset property at all. So when you consider selecting the right database, you have to be mindful whether or not you need those property from ACID. If it is a yes, then there is no question. You have to go with a relational database. Otherwise, you can choose other NoSQL. For scalability, I already mentioned a little bit. Only RDBMS that have like very hard or very, how do I say, very costly in order to scale it up. But the rest, you can scale it horizontally. Typical latency for a relational database is pretty low. And you could imagine that with the vector database as well, very vector database. But if you look at who are slowest, it is pretty, how do I say, surprising to see that document, key value, and search engine are slower, right? Because they are not designed to search very quickly unless you have a very good type of the database design. So typical use again for the relational database, if you remember OLTP is online transaction processing. And for integrity, so if you need integrity, you need online transaction processing that you will be transact a lot. For example, I talked about, like, remember we talk about phone company, right? You make the transaction like every millisecond. So that in that type of thing, you probably need to use relational database. And the rest would be different, like document would be semi-structured apps. Key value would use caching assertions. Search engine is very good at text search, and vector is good at semantic search and AI. And don't use it, or worse at unstructured, it's just the reverse of the line before. And the typical examples, you probably already saw it from the last slide. And I'll skip this because it takes time. Now, one of the thing that we need to discuss is that whether or not you can use AI for database, right? Or particularly in this class. And my answer is yes, you can always use AI, and I actually encourage you to use AI. However, I would encourage you to use AI with responsibilities. What does it mean? I said you use AI as a learning assistant, okay? Not an answering machine. Oh, ฟังครูก่อนนะ not an answering machine. It means that don't use AI to just do your homeworks without understanding anything. So what I would like to suggest you is to understand, and understanding and reasoning comes first, right? If you use AI, you must still own the work. So I would say again and again and again that although you use AI, you are responsible to review, revise, and make sure that it is your own work. Most of the time, AI would suggest something that is, garbages, and you have to be able to pick those garbages and then, fix it before you submit your work. So you may use it for explaining the concept, understanding errors, or brainstorming your ideas, but you may not use AI to submit your work that you do not understand or replace your work, your own design decision. So the responsibility rule is that anything you submit is treated as your own work. And you must be able to explain every query and design of your database. And AI actually help, but does not remove the accountability. So finally, I said the AI actually generates code, but the database design reflects the understanding that you know your work, right? So, oops, how come I don't? Actually, I have another. I tried using ChatGPT and Gemini to generate the database design, and then I'll keep that because during the design I'll show you what happened there. So basically I can tell you right now that let me ask you this. Do you think using AI would be better at the design of the database or with the coding of the SQL? Who says with the design? Okay. Who says SQL coding? You're good, right? It's kind of obvious that with coding using SQL is good, but what I found using AI for SQL coding is that a lot of time you don't know whether or not those codes are secure. So if you do not know whether those codes are secure, then it's a big problem, right? So make sure that you review your code extensively before you actually use the codes commercially. Right. Okay, so that's the end of the chapter 1. Anyone has any question? Not yet? Okay, let me check if I'm still sharing the. Oops. I see. เมื่อกี้ครูลืมแชร์ป่ะในซูมมีใครอยู่ในซูมป่ะแชร์อยู่ใช่ไหมเมื่อกี้ก็แชร์ใช่ไหมตอนที่อัดรอบแรกก็แชร์อยู่ป่ะโอเคเมื่อกี้นี่ครูใจหายนึกว่าลืมแชร์โอเคค่ะ thank you I was afraid of whether or not I was sharing the right ones anyway so if you don't have the question yet then you can save the questions and ask me at any time or at the end of the class as well so let's go to this because I have like 60 pages here and I'm afraid I cannot finish it in time so let me start now oops not that I want to do Hmm? Okay, so this chapter is dealing about is to deal about data modeling using entity relationship model. Last week I mentioned a little bit about entity relationship model. So basically, with the entity relationship, all it does is to work on a model with relational database. So this class is relational database or SQL only. It doesn't have anything to do with no SQL. All right. So we'll go through the example of a company. So to see like a very simplified company, how does its database may look like, and then within that or from that particular example, we will go through the ER model. How could we model the database using the ER diagram? So we'll talk about the entities and attributes. These are the words that we talked about already last time, but now we are going to put them in use. And we'll talk about entity types, value sets, and key attributes, relationships and relationship types, weak entity types, role and attributes in relationship types. Then we'll talk about the EI diagram along with their notation. And then we'll look at the ER diagram for the whole company schema. And then we'll talk about alternative notations. All right. So these are the outline of this lecture. So let's begin. Let's say that, when we talk about a database application, we always mean that it is an application using the database, right? Using the database. Okay. So it's a particular database, for example, University Registrar System, and the associated programs that implement the database queries and updates. So what I mean is that you probably have the DBMS in use, you have the data in there, but it's not necessarily ready to use, right? So you probably have to write an application to connect everything together or to cover all the transactions or need all the usages that you intend to. For example, if I talk about a bank application that keeps track of customer accounts, it would include a program that keeps track of customer accounts while you have the data within the database, right? So you keep track of what the consumer or customers doing their deposits, doing their withdrawals, that kind of thing. So those are the data kept within the database. But in order for a user to be able to withdraw, you probably need to write another application on top or to cover the database itself. So part of database will require a design, of course, the implementation and the test of the application programs before it is being launched to be used in the world. All right. So there are two methodologies that I would like to touch upon. So that these two things is like one is the database design methodologies and another is the software engineering methodologies. They are very closely related. That is why you will have a capstone project that would be the mix between database and software engineering class. So when I talk about database design methodologies, basically it would include more concept with specifying the operation on the database object, meaning that you have the data in the database, right? Then when we talk about database design methodology, it has to do just within the database. We do not talk about doing anything with the application that covers it. We just talk about the database and how it is kept, how it is used, how it is deleted, how it is inserted, and so and so. But in order to go more or further, when you talk about the application associated to the database, then you use another methodology called software engineering methodology. So it will provide more details in the structure that is being used within the application. So when you talk about a software engineering methodology, it is at the application level or at the software level that uses those particular databases. But how, you know that naturally they are strongly related because they have to be used together anyway. So here's the main phase of the database design, just for the design only. So basically, we'll start from this mini world. Okay, from this mini world, we look at the mini world such that if you are working on a university database systems, then our mini world is how students register to their classes, how professors teach classes, how university understand which students are new, which who are about to graduate, so and so. So the mini world would have like constraint or would have the bound of what kind of information, what kind of activities you'd like to perform within that mini world. So when we're talking about mini world of the university database, it doesn't have to do with like banking industry or the, any other thing that is not related to it. Then within the mini world, you see two slides here. Let me take a look at, let me go through this from mini world. Then what you do is that you understand what mini world, the circumstances, the involvement of the people, involvement of the data by working on requirements collection and analysis. So you have to see the users, you have to see the information that was there before, you need to see some of the examples that they have collected to understand what kind of answers or what kind of operations they like to achieve, right? And then after you get all the requirements, you get the database requirements afterward, meaning that now we know what the users would like to do. You need to know what kind of data you have to have in order to perform those requirements. Then after you have the database requirement, you do the conceptual design. So you design like how the database would look like, how many tables there are, how are they related, which information is more important, which information you can leave out, that kind of thing. Once you have the conceptual design, you will write down the conceptual schema, right? Now, after that, you will design a logical step or logical side of the database, like if this data should be kept with hash or using hash, or this index would be using B-tree, or this would be an unordered files or an ordered files that you will keep logically within the engine, the database engine, or the database hardware itself. And the database, the physical design would be how you would allocate the space within the database machine for this type of information to reside at. Which address are you keeping the information? How are they related? How you keep the actual data and the metadata that you could link together. So that kind of thing would be at the physical design level, right? Now, you do the physical design because you have the logical or conceptual schema in order to work on physical design. And once you design the physical level already, you will come out with the internal schema, which you will feed into the transaction implementation there. Now, on the left chain here, you see that after the requirement collections and analysis are done, then you get the functional requirements, right? Once you get the functional requirements, you do the functional analysis in order to obtain the high level transaction specific. So basically this, just this level, I would say that it is DBMS independent. It means that when you do software engineering class, you also have to do the same thing. You obtain the requirement, you obtain the data that you perhaps like know or have examples from the past, things like that. Now, underneath this line, I say DBMS specific. What does it mean? It means that before this line, you don't have to think of which product or which DBMS engine you are going to implement. For example, are you going to use RDBMS or NoSQL? If I am using NoSQL, which ones am I going to be using? Not at the level before the dotted line, but after the dotted line here, in order to perform the logical design, the physical design, the application program design, and transaction implementation, you have to know already which DBMS product you will be using, all right? So when you design without DBMS in mind, it kind of give you freedom of which DBMS you'll be using first. And after you already gain the type of implementation you need, the specific requirements you have, then you'll be able to pick. And then afterward, you need to keep those DBMS specific characteristic in order to design the rest. Right? Now, let's see. One of the example that we are going to go through this time is called the company database. So let's say that we have a very oversimplified requirement set saying that the company is organized into departments. All right. Meaning that, most of the company, you have many departments, right? Like even in the university, you have many departments. But now we are talking just about a very small, simple company first. So let's say a company have many, many, many departments. And we say that, these are the things that you talk to the users, and users said, these are the requirements. You said, for each of the department, what would you like to keep? What kind of data would you like to keep? You said that each department must have the name that is unique by its nature, meaning that no two department names are alike. And then each department also have unique number and a particular employer who manages the department, right? Okay. All these information are arbitrary at the moment, but actually it should come when you obtain the requirement. When you talk to the users, you must obtain this kind of information. Okay. Then within the requirement, it also that we need to keep track of the start date of the department manager. So you talk about manager before that, right? We said that it has to have a manager who is an employee within the company, just one manager. But when you have the manager, you want to know when does that manager start being a manager for that particular department, because you can have the same manager who have been a manager for one department, and then she or he finished being a manager from that department and was promoted to be a manager of another department. So you have to keep track of the date there. And it also said that, well, our department may have several locations, and each of the department controls a number of projects, and then each project have a unique name, unique number, and is located at a single location. So what it means is that although a department may have several locations, for example, I have like a bank. You have many, many branches. So you can have like accounting department in each of the branches, for example. But then you said that although it has many locations, but if you have a project, one of the project must be located within just single location. So these are the requirements that you should obtain from when you do the requirement gathering. Moreover, you have that you obtain the information such that that the employee, each employee, what is important about them is the social security number or identification number per se. You have address, salary, sex, and birth date for each of the employee. And each employee works for one department but may work on several projects. Okay, one department only, but can work for several projects. We also keep track of the number of hours per week each of the employee currently works on each project. For example, if an employee A works for project 1, 2, 3, 4, 5, we want to know if employee A works how many hours for project number 1, project number 2, project number 3, and so on. We also keep track of the direct supervisor of each employee. Okay. And each employee must have a number of dependents. Okay. So for example, in this company, they are mindful about whether or not an employee have dependents, if they have like sons or daughters, they have any one who depends on them at all. If so, they would like to keep them, so basically probably they might have some kind of benefits for their dependents. And for each dependent, we keep track of their name, sex, birth date, and relationship to the employee. For example, maybe father, mother, or, guardian, so on. All right. So here is the example of the ER diagram, ER schema diagram. The full name is ER schema diagram, but most of the time we call it ER diagram or entity relationship diagram for this company database. So let's take a look here. Let me go to. Okay. Okay. Does anyone know if I can use Canva to just like draw some line while presenting? But that's okay. I'll just do this. Okay. So here's the example of the ER diagram. Let's say in ER diagram is E and R, right? So let's work on the E first. E is the entity. Let's see which are the entities within this schema diagram. So you could probably imagine that the entity here are rectangles, all the rectangles, which is employees here. How many rectangles or how many entities do you see in this particular diagram? 1, 2, 3, so employee, department, project, and dependent down here, right? But dependent is kind of different because it has like double line for the rectangles, right? But the rest has only one line. I'll go over the difference there, but you are correct. We have 4 entities here. What about relationships? Which symbol says that it is relationship? Okay, so the relationships are always between or among entities. Relationships only appear if you have something related or some of the entities are related to each other. For example, here, you see that all the relationships are signified by the diamonds here. So for example, in this diagram, how many relationships are there? How many? 1, 2, 3, 4, 5, 6, right? We have 6 relationships. Follow me. We have works for diamond here, which are related between employee and department. We say that employee works for department. I'll go over the details, but I just want to see you to get familiar with the symbols here first. And then we also say employee manages department. And we say that department controls project. So this is the relationship between department and project. But you probably see that between employee and department, there are actually 2 relationships related, right? One set is the works for, another set is manages. But here, control is the relationship between department and project, and that's it, right? And then you also have relationship between project employee. We said that employee works on project, right? So that is the relationship between employee and project. And now, oh, it is. I didn't count it, right? 1, 2, 3, 4, 5, 6. Did I count it? I count. I'll tell you why. Okay. So now you also have the relationship between employee and dependent, where we say dependent is dependent of employee. So that is relationship. Now you have this strange relationship here, which is recursive, right? So it says that an employee may be supervising another employee. So it's a recursive relationship within the same entities. All right. So from this, you can probably see two roles here, supervisor and supervisee. So can say that an employee is supervising another supervisee, or this employee is a supervisee of that supervisor who is another employee within the same company. All right. Now, that is the diagram that we'll be working within this lecture, and then you'll be developing your own ER diagram for your project. All right. So let's talk about the entity and relationships that I just showed you in the diagram. So entities are any objects that you can think of, specific objects or things or anything that you can think of in your mini world. We talked about mini world, right? You said that, well, if you are going to develop a university registration system, then your mini world would be students, teachers, classroom, course. So some of them are people, some of them might be subjects, some of them are objects, anything that you can think of which involve within the data among them would be involved within the same database. So for example, this particular company mini world would have employee, department, and project. All right. And when we talk about attributes, now that is the entity. Okay. Another word that I would like to introduce now is called attribute, which go back to this slide. Attributes are these bubbles, right? These bubbles, or circles or ellipses here. So for each of the entities, okay, for each of the entity, you will have attribute. So attribute are particular properties of the employee of the that particular entity. For example, we have employee entity. So we say that within the employee entity, we have these attribute, SSN, which is social security number, first name, name that includes first name, middle initial, last name. We have birth date, we have address, we have salary, we have sex. Where did this come from? It came from the requirement that you obtain when you do requirement analysis. So and so. So for department, you said, oh, it has many locations. It has name, it has number, but it has many locations. For the dependents, you want to keep name, sex, birth date, and relationship. These are all, this all came from the requirements. Okay. All right. So you know the entities and you know the attributes. And you probably see that the specific entity will have a value for each of its attribute. For example, if you have like name, like John Smith, you have SSN and address, you have sex, you have birth date for each particular one. And now each of the attributes has a value set itself also. For example, this attribute has name, which is a string. It has age, which is integer, or you have subrange or enumerated type and so on. So I would like to draw the relationship between attributes and entities like this. Entities will comprise many, many attributes, right? So when you look at an entity, attributes are inside the entities. Now, for example, on the right here, I have an entity called employee. So employee, you have attribute called here name, social security number, or like ID number. You have address, you have sex, and you have phone number here. Oh, sorry, date of birth here. So each of the employee would have specific set or value set within that attributes for each one of them. All right. So the attribute would be name, would be SSN, would be address, sex, and birth date. But the value for each of the attribute are like John Smith, so and so, the specific address. Okay. Okay or no? Okay, no? All right. Now, like more example of between entities and their attributes. For example, entity number one, E1, would probably like the first person or the first employee. This is employee number one. His name is John Smith. His address is so and so. His age is this, and his home phone is this. And if you have a C here, which is a company here, the Yeah, company, you said name of company is Sunco Oil. Its headquarters is in Houston. The president is John Smith. But if you have company number 2, name would be different, headquarters different, president different, but every company will have name, headquarters, and president. Yes, exactly. But that is a very good note. But within database, you must have them. But for object oriented, you can discard. Right. Okay. Now, the types of attributes that you could have are four types here. One is a symbol type, which is the opposite of the composite type. For the simple type, for example, it's like name or SSN or sex, it means that you only have one value for that specific value of that attribute. For example, here that I have SSN or sex. But when we are talking about composite attribute, it means that it may comprise many of the simple attributes into one. For example, the address attribute may comprise of apartment number or house number, street, city, state, zip code, and country. And the composite itself is called address. So within this, for this example, I would say that address, an attribute called address, is of a composite type if it comprises other attributes. All right. Okay. Now, we can also look at attributes as single valued or multi-valued. When we talk about single valued, it means that that attribute can only contain one information or one data. For example, you could only have one age, right? You could only have one height. You could not have like probably this height or that height. It's not possible, all right? But when we talk about multi-valued attribute, it means that for that particular attribute, it may have many data about it. For example, I said color of the car or previous degrees, perhaps it is possible that, well, this car is not only blue, but it is blue and black, for example. Or if you have previous degree, you probably have many, many previous degrees before. So if there are possible value for each of the attributes type, then you model it as multi-valued attributes. But if you could only have one value for that particular attribute, it is a single value. So when you build attributes, it's either simple or composite. That's one of the angle that you look at. And the angle is that whether it is single or multi-valued. Yes. Okay, let me take you back to this. Maybe it's easier. For example, here we said that each of the department may have many, many locations, right? So if you model it, if you see it from here, I will have like double line around the location, meaning that because I obtained the requirement saying that a department may have many locations. So it means that I have to keep many many values for just location, right? Location number 1 is here, location number 2 is here, location number 3 is here. So in that sense, I will model such that I know I have the double line here, so I know that there will be many, many values, right? But for the single value, for example, those without the double lines, then it's only single value. For example, if you take a look at salary here, it's the current salary, right? But if you want to keep like many, many salaries, beforehand, how much this person has received as salaries, then it has to be multi-valued. All right. Now, for the so that is between sorry, multi-value and single value. But on the other hand, we were talking about composite and here, composite and simple. So if you take a look at this, actually, I'm going to talk more about it, but I just want to bring you back to this slide. When we talk about composite or non-composite, simple is this. You probably don't see it much. Oh, you can see it here. For an employee, you probably have like just one social security number or one ID, right? You have birth date, just one birth date. But we want to keep their name. However, within the name, I want to keep first name, middle initial, and last name, and composite it and call it name. So for name, I said I want a composite called name, which comprises of the single or basic, the simple one, first name, middle initial, and last name, and composite as name. Yes, exactly. And it's nested. Okay. Actually, I have like more update descriptions later on a little bit also. So the composite attribute, like I mentioned earlier, like name, you can have first name, middle initial, and last name. This is another example when you have a hierarchy of composite attributes. And actually you can even have further uh, hierarchy. For example, this one here, I said address, which comprises street address, city, state, and zip. And for street address, I probably have like house number, I could have floor number, I could have room number here, and you can do that so and so. So these are called the composite attributes, which could comprise many of the basic ones in different hierarchy, right? Another example here is the address and phone. This is a complex attributes where you have address, phone. So you have phone, within the phone you have area code, you have phone number. And for address, you have street address. Within street address, you have number, street apartment number, and then out of that, you have cities, state, and zip. So this is a very complex attribute. If you ask me whether or not I like this, I don't. And usually people don't really model their database such that it is very complex. We'd like to have atomic. Right, they are nested. But to make it unnested, there would be a step that we would learn next week to make sure that each of them are simple enough to manage. Okay. It is normalization. Part of it is actually before normalization and then normalization. It is turning the table into turning the design into the table. So in general, composite and multi-valued attribute may be nested, like you said, right? Arbitrarily to any number of levels, although it is rare. Here I'm showing another example, like you have previous degree, which comprises college, year, degree, and field, and you can have many, many of them. Yes. So when we look at the attributes from another angle, we say whether, how that attribute or value of that attribute came from. So if it is a stored attribute, it's like, for example, birth date, it means that the user must enter that information and that data into the database. But when you talk about derived attributes, it means that the user does not enter that information into the database, but it is computed. For example, where does age come from? Do you think in the table? Yeah, exactly, right? So you usually have the date of birth and you have today's date, right? And you operate today's date and birth date, then you obtain the age. Then age would be entered or inserted into the database, which we call this the derived attributes. So if you know that some of the attributes are not going to be inserted by the users, then they are all derived attributes. Now, it is very much possible that we don't have any value for that particular data. Then what we do in the database, we call it a null values. So a null values is a particular attribute that may not have applicable value. Think about it. If I say that I have first name, I have last name, but I don't have middle name, right? Can I say, if you look at the middle name, then we want to know whether or not this person have the middle name, right? If I don't have the middle name and I leave it blank, it probably means that my middle name is blank. Or I put dash in the middle name, it means that, in the database, it means that my middle name is dash. You get it, right? So now, if you want to say in the database that that particular attribute doesn't have any value, we will always use the word null. So when you said null in the database, it means that there is no value associated to that particular attribute. All right.
Should we try as much as possible to not to ensure that null values cannot be constant as required?
Yes. That is the best way to do, but naturally it is possible that probably doesn't have, it must use null anyway. For example, if you talk about address, you know, if you live in a house, then you probably don't have room number, or you don't have floor number, but you have to keep floor number if that particular person live in a condo or apartment, right? So it is very much possible to use null. So null is normal in the database, but the least null, the better. The least null, the better, because there are some harms in using nulls. Actually, I say it here also. Now, I saw already here. And it says that null can be used if we do not know the value of an attribute of the particular entity, but it is possible that the attribute value actually exists, but you don't know it. For example, you said that, well, please enter your height. And then, one of the user did not enter the height. Then actually there is a height for that person, but just that you don't know the data because that person did not enter that particular information. Then you use null. Or the attribute value is not known whether the attribute value existed. You don't know if that exists. For example, home phone, you don't know whether that person has home phone or not. Then you use null. Okay. Now, the harmful effect of null is that when you compute null and null together, it takes a lot of space if there are too many nulls in the systems, right? And if we talk about entity types and key attributes, now I'm uh introducing another term called entity type, right? When I say entities, when you have an entities, many entities, with the same set of attributes, like for example, into one, if we have like student in this class, student number one is one entity, student number two is another entity, but each of the student also have name, have last name, have course number that they take, has their age, has their address. When you have the same set of attributes, we'll group it into entity type. All right. For example, the employee entity type or project entity type. So basically, when I call entity before, if you assume that they all have the same set of attributes, you can safely call them entity type. Okay. So basically, the collection of all entities of a particular entity type in a database at any point in time is called an entity set, meaning that if you get a snapshot of the database, you have a big database, a collection of entities, and then you take a snapshot, then all the entity type there becomes an entity set, which is the current entity data, in the database. Now, an attribute of any entity type, if they have unique value, we'll call it a key attribute. For example, if you think of student entity type, what would be a unique attribute for student? We probably have student number, student name, student last name. Can student name and last name be unique, you think? Is it possible that it's not unique? It is, right? Because, some may have the same first name and last name, so it cannot be unique. But do you think the ID number or passport number would be unique? Okay, so anything that could be unique for that particular entity, then you call it or you assign it as key attribute. For example, for employee and entity type, we probably use the social security number or identification number of that person as a key attribute. Okay, now, so here's the example for entity type name employee. You have, here is the entity set, which is the current information about that particular employee. You have name, age, and salary as their attributes. So I say for one of the entity, we have entity employee number one, employee E2, employee E3, and these are their associated data within their for each of the attributes. And here are the entity type, name, company with attributes, name, headquarters, and president. And here are the entity set or extension of it. Okay. Now we'll talk about the key attributes a little bit further. For example, if an entity type exists, there may be more than one key attribute. There may be more than one key attribute. For example, a car. What could be a good key attribute for a car? I actually have the answer here already, right? But if you think about car, there'll be two things, right? One is called the vehicle identification number. Have you seen it? It's like you have to open the hood, and then within the hood you see the engine number, inscribed, on the hardware somewhere, right? And then it's very hard to go away. Then those are unique. But think about it. License plate is also another thing that is unique, right? Let me ask you, is it possible that license plate is not a key attribute? Is it possible that there are two same license plates?
No, like after some time of having a new car,
You use the same number.
same license plate can be registered.
Okay. But if we assume that at any point in time, it can only be associated with one vehicle. So when it was used in another vehicle before, but now you move it to another vehicle. So basically it is by that sense, within that sense that it can only be used at one time. Okay. So if in that sense it is unique, however, your point is really good because it can be changed. But the VIN number, a vehicle identification number, doesn't change, right? Yeah. So it doesn't change. So in order to pick the good key attribute, you should pick something that does not change or does not change much. For example, if you are going to use as key attribute, let me ask you this. For student entity type, you probably have like student ID, right? That Jula gave you that is unique, but you also have your identification number, right? Right? The citizen ID, or you have passport. Are they all unique? They're all unique, right? You just pick one. So you can pick any one, but whenever you decide to pick which one, you make sure that it does not change much. But all three of them doesn't change much, except actually all two. But because of the passport, you probably need new passport in 5 or 10 years. So passport number does change, but ID doesn't change, right? And student number may not change, but once you are not student anymore, that number is not useful for other systems. That's a good thing. So it changed in the sense that this person has this passport number for now, and then 10 years later, he has this passport number at that time. It is still unique because that passport number only identifies that person at that time. It doesn't, it's not redundant, but it changes over time. But your ID, like national ID, it doesn't change over time. Yeah. All right. Now, the key attribute also can be composite. For example, the license plate number, if you are going to use license plate number as key attribute, it may comprise, for example, in Thailand, it would be the 2 letters followed by number. And then you also have the province that it came from. I'm not sure how is it in France, the license plate number, can it be anything or is there a fixed structure? Fixed structure? So it comprised of city? No, just number? Mm. Mm. Oh. I see. So there are some structures. I see. All right. Thank you so much. Now, I think that many of the countries at the moment, even in Thailand, now you can design your own license plate number, right? You can request for like just do the word or something like that. Is it legal? Oh, okay. So in many countries, it becomes how do I say, more unstructured. So to me, I'm not going to use like license plate number as key because although it is unique, but it doesn't have any structure, so it becomes very hard to understand. But you know, it changes over time. It may change over time as well. So yeah, use a key. Anything would work, but you should pick like uh how do I say, appropriate ones that doesn't change much over time. Okay, so these are the example of key attributes here. I have a car, right, as a entity type car. And then within this entity type car, I have many attributes. And you could probably see that I underline possible key attributes. I said registration number or the license plate number is unique or is a key. And also vehicle ID is a key. So now I have two keys here in the example above. And here are the example of the attributes and its value set associated to it. 10:25 แล้วเราควรจะเบรกใช่ไหม Okay, let me finish this value set before we take a little break. So when I talk about the value set or the attribute, it could be any entity type that the domain of value associated to it. So you could have like integer, string, boolean, float, enumerated type, subrange, and so on. So for the enumerated type, usually it is prefixed data that users can choose from. For example, if you have a data and you ask the user to choose like which province you come from, right? And then instead of having the users enter the information themselves because it could be wrong or it could be different from one to another, it could be different languages as well, then you have them select particular data, for example, okay, let me give you an example like you have you ask the users to enter their birth date, right? And you ask for month. Instead of having them entering the month, you have them select January, February, March, April, and so on. So it ensures that the data that you insert into the table is always correct or least incorrect. And then this is called enumerated type. But for the subrange, it's the range of the data that you allow the users or allow the database to keep. For example, you could say that for month, you only allow integer with value of 1 to 12. Or for time, you only allow value for certain number that you can enter.
Data types for each specific, let me just map to each specific.
Yes, exactly. Okay. All right. So we're gonna break here for about 10 minutes. Now it's 10:27. So come back at 10:37. Okay. Let me continue. Otherwise, I wouldn't be able to finish it again. Okay. Oh, I know this. All right. Okay. Now, let's take a look at the preliminary design of the entity types. All right. So the entity types here, there are 4 entity types. Before this, I call them entity, but the actual terms in the database is actually entity type. And entity type only says that because of the entity have the same attributes, whenever the the entities have exactly same attribute, we can call them attribute type. All right. So here we have 4 entity types called department, project, employee, and dependent. For department here, you can say that from the requirement that we gathered, we know that department. Okay, wrong page. The department has its name, right? Whoa, this is too big. How do I say? มันออกไหมอุ๊ยมันลบไงอ่ะโอเคอ๋อ Okay, so for each of the department, the requirement said that we have name and number. And it also says that name and number are unique. So that's why you probably see that I use the line here. I draw a line here underneath. So whenever you see the line, it means that that attribute is a key attribute, which is unique. So in this particular example, we say that department has name and number as unique attributes, and they are key attributes. It also have many locations. So to depict many locations there, we said it is a multi-valued attribute, and multi-valued is signified with the double lines there. For the department, we also have manager and its starting date, their starting date. So we have the name of the manager, which is a single attribute, single basic attribute there, simple attribute there, and the manager start date. Now, for the project, we said we have name and number as a key, and we have location. We say that one project only have one location, right? That is why the location here does not have the double line around it. It also has a controlling department. For the employee here, if we write it in words like this, when you like write down the schema, on the left is called the schema. On the right is the ER, the entity relationship. So on the left, when you write the schema, you said name comprise of, okay, name comprises first name, middle initial, and last name. So this is a composite. You can see here that name is actually goes here, right? And then the composite would be the sub attribute under name. So it means that when you have name, you can have the line to draw their sub attributes from that particular attribute, right? Now, another thing to be noted here is the works on. So employee, you have name, you have social security number, you have sex, you have address, salary, date, department, supervisor, birth date. Oh, I missed something. And you have this works on. So works on is also a composite. For works on, you have project and hours. However, works on is also has it also has double line. It means that it is what? When you have double line, it is multi-valued, right? So works on can be many, many times. Finally, for dependent, we said that dependent has employee, dependent name, sex, birth date, and relationship. So those are the information that we will draw. However, if you notice, there is no key in the dependent, right? Because when you gather it from the requirement, you said that dependent has relationship with the whoever related to that dependent, which employee, right? The birth date, the sex employee related to that dependent, and the dependent name. But there is no key in that particular one. So is it possible to have a key for dependents? That's good. First of all, not every employee have dependent, so it could be no. But second of all, whenever you have one dependent, right here, if you take a look at this one, you said that, well, we know the birth date, right? We saw that, okay, this dependent is born on that day. So birth date is not unique anyway, right? Now we know the sex. Sex is also not unique. You know the relationship. Relationship can be mother, father, and so on. So it's not unique, of course. An employee that it is related to also is not going to be unique because it can also relate to many employees if that is possible. And finally, dependent name that may be unique, may not be unique. So basically right here, it doesn't say anything about uniqueness. We will determine how to model this later. All right. But I just want you to note that other than that, employee has social security number as its key attribute, which is unique. Project name has name and number. Department name has name and number as unique keys. All right. Now, oops. So to sum up all the notations from the previous example, you will see that the entity or entity type is rectangle. The one with double line is another entity type, which is called a weak entity. Whenever I say weak entity, it means that that entity doesn't have a key of its own. All right. For example, like dependent, it doesn't have a key, so it becomes weak. All right. The relationship is signified by the rectangle. Oh no, sorry, by the diamond. But if it comes from the weak entity, it is something called identifying relationship. So this only works with the weak entity. An attribute is also an ellipse here, but if it is key attribute, you underline it. And if it is multi-valued attribute, you do the double lining, all right? Now, further on, if it's composite attribute, you can draw an attribute and then you can draw a line to include other attribute to that attribute. Now, I didn't mention this earlier, but I did mention the word derived attribute. But in order to depict a derived attribute, instead of the simple single line, we use dotted line to signify that this is a derived attribute. And you remember, right, that the derived attribute must be computed from other values in the database. And then these are extras that we haven't touched, but we will be touching on this a little bit more. So this is something called participation of E2 in R1. What it means is that we have entity number one, we have entity number two, and then we have relationship between entity one and entity two. So participation would be signified by single line or double line. When we say double line here, E2 and R, it has double line, it means total participation. What it means is that it has to have value. It cannot be left null, right? Now, the next term is called cardinality ratio. For cardinality ratio, you probably hear it a lot. It's like one to many, many to one, many to many. So within the database, we signify it with the letter and number here, like one is one, n is many. You can use m or n. So right here we have the relationship E1 and E2. We have a relationship R to connect E1 entity and E2 entity. So then what we call here is that we have one to many relationship. Okay. So it's a cardinality ratio of one to many for E1 and E2. Okay. E1 is entity number one and E2 in the relationship R. Now, another way that we can depict this is another notation. It's called the structural constraint, which is the min or max of participation of E in R. So it is similar to the total participation or not total participation here. But instead of doing a one line and double line, we say number here, like 0 to n or 1 to n, so and so. We will see more in the next slide. So I already circle the entity types, which are employee, department, project, and dependent in this picture. Can you see which one is the derived attribute? Derived attribute. Yes. Okay. Right. So the only derived attribute here is number of employees, right? So within the department, we want to keep name, location, and number, but we want to compute how many employees are there in the department as well. So that number would be computed according to which employee within each department, and then we keep that attribute separately, right? Now, let me ask you, should age be derived or should age be entered? Derived, right? Okay. What else may be derived naturally? For example, if you do address, all right, if I give zip code, then you will have the selection of what can you enter within the same zip code, right? So this zip code would belong to like this province, and then this particular areas in the province and be given. So that could be derived as well. Now, I want to talk a little bit more about relationships because we already talked about entity and entity types. Now it's on relationships and relationship types, which has the same, it goes together. So a relationship relates two or more distinct entities. I said two or more. So it is possible that relationship may relate three or more entities with a specific meaning. For example, I said employee John Smith works on a product X project, or employee Franklin Wong manages the research department. So you can see here that the relationship between, for the first example, employee and project. And the next one is the relationship between employee and department. Now, if you have relationships of the same type, they will be grouped into a relationship type. For example, the works on relationship type, like employee and project participate, they can be grouped together. And managers relationship can also group together, right? We'll see the example on the next slide. And if you have the degree of the relationship type, it means that we are looking at the number of participating entity types. For example, if the relationship type is related between two entities, it will be called binary relationship. But if it's more than two entities, it will be like n-ary relationships. So if it's three, it will be ternary relationships. If it's more than three, it will be n-ary relationships type. All right. So let's see this instance. Okay. In the work for relationship, I circle it on the right here. So works for relate employee and department, right? You have employee on the left, you have department on the right, and we say that an employee works for department, right? In that sense, if you look at the possible instance here, you say that employee E1 works for department 1. Employee E2 works for department 2. You will see that each employee can only work for one department, right? But for each department may have many employees. So this type of relationship is called one to many, meaning that one employee works for one department. But if you look at the department, you have many employees in one department. So on this side, relationships here would be one to many. Okay. Now, so this is a relationship type works for example. Okay. Now, if you look at the relationship that is called works on, it's also the same set, right? Between employee, oh no, sorry, this is another set. Employee and project. So between employee and project, there is a relationship called works on. You can see here that one employee can works on many projects. For example, employee number 3 works on P2. He also works on P3 and he works on P4. But the project that he works on is a different one. For example, E3 works on project P2 with R4. Probably it's like the name of the project, right? And E3 works on work one project, not the name of the project, works on project P3 and P4 as well. So in this regard, is it one-to-one, one-to-many, or many-to-many? You can see here, P4, you have employee E2, and you also have employee E3. So in these relationship, is it one-to-one, one-to-many, or many-to-many? Who say one-to-one? Who say one-to-many? Who say many-to-many? Okay, exactly. It is many to many relationship here. So you can see that I did pick M and N here. So the line here, you can see M and N on the line. M here, N here. So it means that project can have many employee. An employee can work on many projects. Okay. Mm. Oh, but back to the one before. We say an employee can work for only one department. Remember? But a department may have many employees. So that one is one too many for sure. But look at where you place the one and where you place the N. All right? Where you place the one and where you place the N. You can see that the department can have many employee. So the N side would be on the employee side. But employee can work for only one department. That is the number one on the department side. Can you see that? You saw that, right? But now let's take a look at another thing. Between the works for you have two lines connect to department employee, and they are both double line. What does it mean? It means that an employee must work for the department. They must work. It is not possible that one employee does not work for anyone. Right. Yes. And a department must have employee. So at least one. So that is called the total participation. But if you compare that with the next one, manage here, I haven't touched manage that much, but if you look at the example here, I say that an employee, you have between employee and department as well. You have managers here. You said that one employee work for a department, but it is not total, right? So it doesn't mean that an employee must be managing the department. So it means that an employee may manage a department, but a department must have an employee. That is the meaning of the double line on the right side. All right. And the one and one here, it means that the department must have one and only one manager. An employee, if he or she is a manager of the department, he or she can only manage one department. Get it? Okay, no? Let's take a look at the next one. Okay, so now I'm going into more detail in here that for the same pair, employee and department, there may be more than one relationship. So you will see that for employee and the department, you have two types of relationship. One is called works for, and one is called managers, right? So it's more than one relationship type, two types of relationship here. Now, for each type of relationship, you write different type of relationship only when you want different meaning, right? Because here, works for and managers has different meaning, and it also determines the one to many, many to many, so the cardinality ratio or the participation as well. So they would be designed according to the meaning of the database. Okay. Now, the relationships type in this diagram would be 6 of them. Works for, managers, control, works on, dependence, and supervision. So let's take a look at the supervision. This is the strange one because one of the strange ones because it actually circulate back to the same one. So it is a recursive type. Okay, we call it a recursive relationship type. So both participation are same entity type but in different roles. So here, the supervision relationship between employee here, you have like employee and supervisor and supervisee, right? So in the if you take a look at the lower figure here, the first role participation level with number 1, and the second would be number 2. All right. So it means that you have the supervisor and supervisee. How you model it, you can number it like the instance below, or the other thing you can do in the ER diagram, you write this thing. You will write this role connected to the line here. All right. So this is how it is modeled in the ER diagram. Oops. Now I talk about this already, that the relationship types of 2-degree will be called binary. So of 2-degree, how do you know about it? Because if it connects to two entities, then it's 2-degree. If one of the relationship is connected to more than two, then it will be n-ary, like many. But if it's three, it's ternary. So you can only have like binary, ternary, or n-ary, right? But usually, I just want to stress that if you have like many, you have n-ary, it's not equal to n of the binary relationships, right? Now, this is the example of ternary relationship when you have the entity called supply, and then you have the entity that you want to connect to oh, sorry, you have this supplier. Let me draw this for you. Okay, you have three entities. Supplier is another one entity type. Part is another entity type. You have project as another entity type. All right. Now you have ternary because supply is connected to three separate entities type. All right. Now, say again. It depends on it could be one to one, one to many, or many to many. Depends on how they are related. For example, if you have one supplier, if you have one project, right, and then the part comes from the same one, it could be anyone. It could be one to one as well. But for example, if supply number one is related to only one supplier for one project, and only one part, then it is one to one. But it is possible that you probably have more than one. For example, this doesn't have more. So this, if you have this line, it means that this one is related to one supplier, one project, but two parts. All right. So it could be one to one, one to many, many to many, depends on how they are related. But if you take a look at the supply alone, it's actually a one to one because it's just one line to each of the entity. Okay. Now, the relationship type that we take a look at can also have attribute. For example, here we have works on, and you obtain the requirement from the users already that you have an employee works on a project. Okay. And if you take a look at these, you can say that an employee can work for many projects, and and each of the project can have many employees. But when an employee works on any project, you want to record how many hours they work on each of the projects, right? So we can have this particular one here called hours, which is the attribute of that relationship. It's not attribute of an employee. It's not an attribute of the project, but it is an attribute of the relationship co-works on. So it only appears whenever that relationship happens. Okay. So for this particular diagram, you say that an employee must work on at least one project, and a project have to have at least one employee because of the double line there, right? Now, but if you have this happen, you have to record number of hours that they work on that particular one. And then I'm not going to write much, otherwise I have to do this all the time. Okay, we talk about the cardinality ratio, which is one to one, one to many, and many to many. I like to expand a little bit on that. And we also talk about the participation constraint. If total participation is a double line, another one that is not total will be called partial. Okay, so when we talk about total participation, it is mandatory. At least you have to have like one set of data from that particular relationship. But if it is partial participation, it means that it could be zero or it is optional, right? it really based on your design. For example, from the requirement that you get, you can say that if you want this is everything that you determine by the requirement of the system. For example, okay, let me give you this example. If you have courses in the university, right? And you have students in the university, and between student and course, you can have the relationship called register, right? You have student register for the course. All right. So it really depends on the requirement. If the requirement say that every course must be registered by at least one student, then it is a total participation. But you say that if it is possible that you open the course, but it's okay not to have any student registered to that course, then it is a partial participation. Partial participation. You know what I mean? And vice versa. If you say you have a student, if you have a student in the university and you say, if you are a student, you must register to at least one of the course, then it is total. But you say that, well, it's okay if student doesn't register. So it is not forced. So it's partial. So partial would allow zero or no information happen there. So information happens when I'm talking about the relationship. So if that relationship doesn't happen, would you allow that relationship to happen or not? If not, then it is, if you force it that at least one student must register, then it is total. But if you okay that it doesn't mean that every course must be registered, then it could be partial. So it comes from the design alone. So now this is the instance from like one-to-one, one-to-many, or many-to-many. When we say one-to-many, it could be many-to-one. It's the same thing. All right. So one-to-one, you can say that an employee manages the department. This is an example from the requirement as well. You can see here. I think this is a good picture. If you see one-to-one relationship here on the left here, does it mean total participation? You can see it from here. Because if an employee must manage department, it means that every employee must have the line connected to department, like the second one. Yeah. So if the constraint on this say that employee must manage some department, then E2, E1, E2, E4, every employee must have the connection with the department through managers. But here you can see that employee works for department, although it doesn't say anything about total or partial in here, but you can actually take it from the diagram that, oh, since every employee must work for department, right? There are lines connected to it for everyone. So it means that this is a total participation. But in terms of the cardinality ratio, one-to-one, one-to-many, or many-to-many, you take a look at whether or not it is allowed to have many connections to that particular entities. So like the one on the left, you can see that department has only one employee as manager. An employee only have one department when they manage it. So that is one-to-one. Now for one-to-many, you can see that employee works for many departments. So, or you can look at it both way. The other way you can say is that for one department, they can have many employees. So it means that, particularly from the department side, it is one-to-many because you can have many employee works for that department. You can see lines here, right? Now, from many-to-many, it's like both ways. One employee may work for many projects. Each project may have many employees. But I said may, right? But in this third diagram here, do you think it is a total from this diagram? You think it's total or partial? Who say it's total? Who says it's partial? Who says not sure? In this, it has to be total because it assumes, well, I assume that every employee, you see that every employee is working on some of the project, right? And every project has employee in it. So it's a total participation. Okay, because if you say like E2 is working on project P1 and project P4. And then you can take a look at P1. In P1, you have E1 working for it and E2 working for it. So it allows many employees to be in one project. And on this side, you allow each employee to work in many projects as well. So you can see lines like from E3 here, you can see many lines out of E3 to connect to many of the projects. Yes, exactly. Exactly. It also comes from the requirement that you want only the relationship like one-to-one, like you obtain the information that, oh, if I have an employee, I would only allow this employee, if there is a manager for the department, I can only have one manager. I would not allow many managers. Or if I say that if there is an employee who is a manager, he or she can only work on manage one department. I would not allow one manager to work on many departments. So it comes from the requirement, and then you model such requirement in the database such that it's one-to-one, because I only allow one manager for one department, something like that. Now, this is an alternative min-max notation, which actually mean the same thing as the total participation plus cardinality ratio, but we specify it differently. So in this type, it is called the this is alternative. Let's see what it means. So it would specify on each participation of entity type, just like the one before, but instead of saying double line and the one to many, many to one, we'll just say minimum and maximum. So it is called the min-max notation. Here, I'll show you how it is done. So for employee managers department, if you remember correctly from the last one, oh, this one, I changed it a little bit though. Oh, no, this is the same one. Okay, if you read this, what it means is that an employee manages department, right? But you now have 0, 1 and 1, 1 here. What it means is that for a department, it must have one. So the minimum is I have to have at least one employee who manage the department, and at most one. So minimum and maximum. อันไหนคะ This one? Yes, because when we talk about relationship, the relationship would connect between two entities, right? Or more. Yes. So you have to look at both sides. But when you determine whether it's one-to-one, one-to-many, you have to take a look at both sides. So there are two, you have to consider both ways. So for example, on the second one here, you will see that one employee can work for just one department, right? So that is the letter, the one for sure. But on this side, you can see that each department can have many employees. So that's many for sure. But now the question is that where do we place that one and where do we place that many? So if you take a look at this works for, right? You can say that this is the relationship works for. So employee can work for just one department, and a department can have many employees. You place the letter one, the letter N here, because one department have many employees in that. Okay, so you can have many employees coming out of employee. But here, for an employee for work on a department, you can only have one department that you work for. อันนี้เก็ตไหม You're talking about total or partial, right? Okay. Actually, when I present this slide, I wasn't intending to talk about total and partial, but because the question came up, so I just want you to take a look at the diagram. So when I talk about total and partial, it means that uh if it is mandatory that an employee must work for every department, you will surely see that every employee must be related to, no, this is not works for, this is managers. If we say that an employee must manage a department, you will surely see every line coming out from employee, right? Mm. But then if you say that each department must have an employee, you will see the line come out from every department at the same time. So it means that this one is not mandatory because not every employee must be managing a department. That's why you can see some instances that does not have the relationship called managers. However, for this one, the second one, you can see that or you can somehow implies that because you see that every employee must work for department, it means that you force it that every employee must work for at least a department. And you also see that every department has a line connection to the employee. You can say that, this may be partial. But the fact that we model the database to be partial or total participation, it all it all came from just the requirements. Let me ask you this. Okay, let's say that if I'm saying that it is possible that I have an employee who doesn't work for any department, how would I change it? If I say that, well, it's okay for employee not to work for any department, it means that let me give you an example. So I said that uh employee one here, I will not allow this, right? I delete this line, for example. So is it still one to many and many to one? It is, right? But it is no longer total because I allow that an employee may not work for any department. Okay. However, if I change this, I said that, well, I also allow that some of the department, I delete these two lines. I said that, well, any department can be on its own without a manager. Then I say that the department connection, to works for here, I allow it not to happen. So this is also a partial. So it could be, so for these two to combine, it will be partial and partial on both sides. And it's also, but it's still one to many. So what the fact for one to many doesn't change. Yep. อันนี้ชัดขึ้นไหมอะได้ไหม Okay. All right. Okay. Okay. So this min max is actually very similar to what we did, but it's another notation. I'm not sure which one is easier to read for you. So this is the same thing. I have employee and department, and the relationship is called managers. So if I say 0, 1, and 1, 1 here, it means that department must have at least one. Let me show you this. At least one. Oops. Okay. And at most one. So minimum and maximum. And then between this, I say that an employee, if I say 0, 1 here, what does it mean? It means that an employee may or may not work because minimum is 0. So number of department that this employee is managing can be 0. So it means that he may not be a manager. Or if he is a manager, he can only manage maximum of 1. Exactly. Right. So that's a good one. So if I change it a little bit, I said that, well, a department may or may not have the manager. What would I change it from here? How would I change it? So it'd be 0 and 1 on the right, right? Exactly. Okay. Now let's look at another example here. I said an employee can work for exactly one department, but a department can have any number of employees. And I said 1 and 1 in here. So it means here that an employee must work at least one, right? And at most one department. But for each of department can have at least one employee and n คือ at any number of employees. So many employees. Let me change this. The min-max notation allow you to do more. I can say 0 and 100. What does it mean? Exactly. Okay. So if it's min-max here, the department can have at least 0 employees. So mean that you do not have at all. But if you have employee, you cannot go over 100 employees. All right. So this is a min-max. So if you write in min-max notation, you don't have to have the double line or single line, right? Because it's included in the minimum already, right? Minimum of 0 or none, right? I mean, zero meaning the single line. And if it's more than 0, it's the double line, right? And then the one to many is also depicted. So it's only one notation here. So I'm showing you the comparison between the two. Oops. Oh, I have to move something here. I'll do it later. Actually, this one to n is here. I want to replace this, but it's on the wrong one. Anyway, so the one on the right is the one that I use as the example, and the one on the left is another thing with the min-max notation, right? I think I have to fix this as well. This should be a single line. All right. Now, the other thing that we still have is the weak entity type. So when talk about weak entity type, it is signified by the double line. So you can see the dependent here. The dependent has double line on its entity, so it is called weak entity. But the problem with weak entity is only happens when it does not have a key attribute, like I told you before. So in order to identify which dependent it is, it has to be connected to an employee, right? So in this case, a weak entity must participate in an identifying relationship type. So the relationship type that it is related to is the employee, and it must be a strong entity type, not the weak one. So entities are identified by the combination of a partial key of the weak entity type itself and the particular entity type that it is related to. So what it means is that if you take a look at the dependent here, I have the dotted line under name. You can see that, right? But name is not actually a good attribute because it could be duplicate, right? So now if it duplicates with the other people, it's no longer a key. So in order to make it a key, we must know this name is related to which employee. Then we assume it can be now unique because employee, you have social security number, which is unique for sure. And then you link that social security number from employee to this dependent. So it becomes unique. But here I assume that each of the employee doesn't have, the same name for their children, right? For their dependents. All right. Okay, so this is the meaning of the weak entity types. Okay, let me tell you once again, weak entity type is always signified by the double line here around the entity. But if you take a look at its relationship, it must also be signified by the double line as well. So the relationship that comes out of a weak entity must also have the double line to signify that it is pointing to the identifying entity that it relates to. All right. Now, if we take a look at this a little bit further, you can see that an employee, have the dependents, right? Now, I have the single line here and double line there, and there's one to many. So it means that the employee may have many dependents, right? Okay. But does every employee must have dependent? No, because I have single line here. But if you look at the other side, if there is a dependent, it must have employee because there's a double line there. Okay. And it's one to many because an employee can have many dependent, but dependent, right, employee. Okay. Where am I? โอเคแย่ละไม่จบแน่เลยอ่ะเดี๋ยวพยายามให้จบก่อนอ๋อครึ่งชั่วโมงได้นะอ่ะ okay so this is another example of a bank of a bank database very simple it's not the real like whole database that you can use at any branch but just want to simplify it a little bit from here let's read the ER diagram together how many entities are there in this one how many entities bank is an entity, bank branch, you have account, you have loan, and you have customer, right? So let's say in this one, how would you read this ER diagram? You can, if you can read it starting from anywhere. So whenever you have an ER diagram, you always take a look at any of the entity and you say that, okay, I have a bank, and a bank has many branches, right? I can say that one bank can have n branches, so many branches. But yes, so a bank branch can have only one bank, can belong to only one bank, right? But however, this one is modeled as a weak entity. So it means that by branch number, it cannot identify with unique number. So it has to belong to which bank. So it's obtain bank code and branch number to identify exactly which bank and branch that one is. All right. But okay, the question is, can I model bank branch as a strong entity? If, okay, if bank branch it has a unique identifier, then you can actually model it as a strong entity. All right. Now, if you read it further, you can say that each of the bank branch would be connected. For example, here, bank branch, you have accounts connected to account, and then you have loans connected to loan, right? And then account and loan comes from where? You come from customer. If customer is taking out the loan from the bank, so customer is related to that loan account, where that loan account is related to each particular branch. And this is also the same. If it's not a loan account, but it's a deposit account, then a customer is related to the regular account and account is related to the branch. All right. At the bank, you have the attribute called code, name, and address, and bank has code as its unique number. For account here, you have account number as key, which is unique, and you have balance and type. Now you would know how much it is for the balance and type. You have to connect that to particular customer there, and that is also the same as the loan account. And for customer, you have social security number, you have phone name and address, and you use SSN or social security number as its unique identifying attribute. Not necessarily. For example, if you have a branch in Siam Square, you probably have number like 12, 13, 14. And the other bank can also have that 12, 13, 14, but it's not the same bank. Just to give you the bad example. So you can, so I can play with it, like, this could be changed, or how can you make it better? So you can see from here already, like you mentioned, when you model or when you design a database, it could be bad, right? So the design process, actually, you have to be very mindful of what you are going to present and how is it going to be very efficient when you use it. So that is the beauty of the design of the database. Now, there is another type of the model called Enhanced Entity Relationship Model, the EER. When we talk about enhanced, we talk about subclasses and superclasses. And these subclasses and superclasses are usually mainly for the entity itself. So when we say that entity type may have additional meaning or subgroupings of its entity, for example, I have here, let me show you here. Oops. Okay, I have here an entity called employee. Okay, now follow me, right? You have employee here, but I want to have subtype of employee, right? I have subtype or subclass. I say that I have 3 types of employee called secretary, technician, and engineer. Why do I do this? I said that if I have secretary, I want to know his or her typing speed. If I have technician, I want to keep technician grade. And if I have an engineer, I want to know their engineering type. So it means that for the same particular one, the same class or the same entity, when I want that same entity to have a little bit different attribute, I can also model it as subclass and superclass, like the example here. All right. So the employee now will be called a superclass, and the secretary, technician, and engineer will call subclasses of superclass called employee. All right. So this is the relationship called subclass and superclasses of the entity. Right. Now, when you do the subclass and superclass, we will read it in the database as a is a. So we call secretary is a employee, technician is an employee, engineer is an employee because they are subclasses of employee. So the entity that is the member of the subclass would represent the same, attribute, they'll take the same set of attribute from its superclass there. For example, here we have employee with name, social security number, birth date, and address. It means that that subclass would also inherit all the property of its superclass. So every employee, although they are secretary with typing speed, they also inherit all the attributes from employee. All right. So an entity cannot exist in a database merely by being a member of a subclass. It must also be a member of a superclass for sure. Now, what happened is that, what about the superclass? Is it possible that the member, naturally, okay, think about it. Is it possible that a member of the superclass called employee is not secretary, not technician, and not engineer? Is it possible? It is, right? So naturally, if we model it that way, it means that, or at least from this diagram, it means that an employee may not be anything, but if he is a secretary, keep the typing speed. If he is a technician, keep T grade. If he is an engineer, keep engineering type. But it is possible that if it's not any of these 3, then just keep the attributes above. All right. But now there is a member of the superclass can be included as a member of any of its subclass as well. For example, here, a salaried employee here, that is it's a possibility that this salaried employee is a manager, or this salaried employee it could be a subclass of an engineer and a salaried employee. You know what I mean? So there are two ways, how do we say, two branches here that you see from employee. We categorize employee by their job, and on the other side, we categorize the employees by their salaries or pay, or like wages. So it is possible that one employee can be an engineer and salaried employee. All right. Okay. So again, it is not necessary that every entity in the superclass be a member of some subclass. But if you are a member of the subclass, you must inherit everything from the superclass. So it is, sorry? It is exactly the same. Yeah. Because the concept of subclass, superclass is actually comes from object-oriented. Right. Now, yes. A member of the superclass and not a member of subclass, yes. For example, I may have an employee, let's say me, I'm not engineer, I'm not technician, I'm not secretary. On this side, yes. But I'll talk about this a little further, but you can see from here, I have the single line here. So when I have the single line, it means it's okay for me not to belong to any of this. So it means, let's say that I'm a doctor, like medical doctor. So I don't have anything further to keep. So just keep the information for attributes up here. But on the right side here, you can see double line. When I say double line, usually it means you are forced, right, to do something. So in this case, I say that one employee must either be salaried employee or hourly employee. So if you force it, it means that that particular person must be either one. So then on this side, it means that every employee must be either one of this. Okay. And actually, you can probably see another notation, the letter D. It means something else too, and I will talk about it a little bit more. All right. But basically, yes. But it depends on how you model your database. Okay. Okay, what if I say that not everyone have to be salaried employee or hourly employee? For example, I might have an advisor who does not have any salary, for example. How do I model on the right side here? I can just remove this double line, right? So it becomes a single line. So it means that one may be our hourly employee, salary employee, or not, right? Like no salary at all, if that is possible. But if your company said you only have two options, you are only paid by hourly or you are paid by salary, then you model such that it belongs to that side. All right. Now, the word specialization is actually a process. And it is a process of defining, the set of subclass of a superclass. So the specialization would go from parents to children. So you would determine the parents first. So in this case, it's a set of subclass. If you have the subclass, it will belong to the superclass. You have the superclass there, you determine what kind of subclass are possible. So the set of subclass would always be based on some distinguished characteristic of the entities in the superclass here. For example, if you see what I circle here in orange is called subtype. All right. So this subtype, called job type. So this job type would say secretary, technician, or engineer, or otherwise. So whenever the job type says secretary, you will keep the typing speed for that particular person. If the job type say technician, you keep T grade. If job type say engineer, you keep engineering type. But if job type says other things, you don't keep these three extra extra ones, but just the attributes above. All right. Okay. Now, furthermore, what we can do is that you can have several specialization of the same superclass. For example, I have another specialization here, right? Salary and employee. And I said that salary and employee belong, can have someone belongs to here as well. So what it means here is that the subclass can participate in specific relationship types as well. Okay. What it means is that I have employee here, right? And then I have subtype on the right, say an employee must be hourly employee or salaried employee. And I say only the subclass that is called hourly employee can only belongs to trade union. You see the relationship here, right? So what I'm saying here is that you can have the relationship that only subclass belongs to. So it means that not every employee can belong to trade union, but I would only allow subclass of employee who belongs to trade union. All right. So this is the example of the further specialization. Now, when we have specialization, you have the reverse process called generalization, but it's actually the same thing. It just depends on how you are familiar with. You like to go from, parents to children or children and group into parents. It's okay. When you go from parents to children, the process we call specialization. But if you go from children and then you group it into parents, you call the process generalization. All right. Let me give you the example here. You can see above, you have car and you have truck, right? Now you see that, hey, car and truck have similar or actually exactly the same set of attributes. So you say, let me group these and call it vehicle. You see that? So the generalization would say that if you see that two attributes here, I have two sets of, I have car. Car have number of passenger, very similar, right? Numbers, let me start with other thing. Car have vehicle ID. Truck also have vehicle ID. Car have license plate number. Truck also has license plate number. Now, car have price. Truck also have price. But truck has number of axles and tonnage. But car have number of passenger and max speed. So you have some similar attributes here, and you have some different attributes here. What you want to do is that, well, since most of the attributes, you say that many of the attributes are the same, why not group them? So when you group them into vehicle, what you do is that you still have car and truck there, but you only have attributes that are different, the different attributes at the subclass level, and you have the same attributes, the duplicate attributes at the superclass level. So finally, it became the same thing, whether you do it from generalization process or you do it through the specialization process. It's the same thing, right? Meaning that the subclass, of the superclass will also inherit the attribute from the superclass, plus at subclass level, it has its own attributes there, extra attributes there. Same thing, but just reverse process. Okay, now we have the constraints that we can show on the specialization and generalization here. For example, here, an employee can be secretary, technician, or engineer. So I'm doing like more more information for each step. Now that this each step, I can say that if there is some of the attribute that determines type of the subclasses, we will call it the predicate defined or condition defined. So it means that if we can determine exactly those entities that will become members of each subclass by some condition, so it is condition defined or predicate defined subclass. For example, here, if you take a look at the diagram, oops. If you take a look at the diagram here, I say from this one, I say that, well, I will know it from job type. So job type is actually one of the attributes here, right? But if I want to model such that I say that from job type would determine the subclass, I will write down job type along the line from employee before it reaches subclass. And then you will also write down the condition here that if job type equals to secretary, go this way. If job type is equal to technician, goes this way. If job type equals to engineer, then you go this way. So what is a predicate defined here is job type. All right. Okay. Now, if you don't have anything to determine, which type, if you don't have the predicate defined or condition defined, it may be something called attribute defined. So for attribute defined, it says that if all subclasses in the specialization have membership condition on same attribute of the superclass, the specialization is called an attribute defined specialization. For example, the attribute is called the defining attribute of the specialization. If job type is a defining attribute, here, job type is the defining attribute. So this is the attribute defined specialization. All right. It's just that the name of the specialization will be called attribute defined specialization. However, if there is no condition that determines the membership, the subclass will be user defined. For example, you allow the user to identify like what if they are secretary or technician or engineer, and then you keep that information later. That example would be something like this. Oops. Let's say that if you do not keep job type, then you don't have anything here, right? So it means that when you use the system, you ask the user whether or not they are secretary, whether they are technician, or whether they are engineer. When they said yes, then you said keep typing speed or key typing speed in. If it says technician, you said key your T grade and so and so. So you will manage it at the user defined level, right? Now, I'm talking about the next thing that I mentioned a little bit earlier, which is the D and the O here. You haven't seen the O before, but now I'm gonna tell you about this. So there will be an D and an O, which is a constraints on the specialized generalization. The D would be called the disjointness constraint. If it is specified by the D, or otherwise it would be an O. All right. So the disjointness is this. It on superclass and subclass, okay, it says that if subclasses of the specialization must be disjointed, all right, it means that disjointed is like this. It means that you can only it is disjointed. You can only choose one. So it means that, for example, here, employee disjoint here, secretary, technician, and engineer. You can only be secretary or technician or engineer. You cannot be technician and secretary. You cannot be combination of any of these, just one. But if you say overlap or an O, you can be both. You could be either or both. Okay, so it's actually by its name. So O would say that it can be overlap. D, you cannot overlap it. It's one or the other, right? You just pick one at a time. You cannot be the combination of the choices of the subclass there. Okay. Another constraint is called completeness constraint, which is the same idea as the total or partial participation. So the total specifies that every entity in the superclass must be a member of some subclass, and that would be signified by the double line. But if it is not mandatory, then there will be a partial completeness. So it would signify by a single line there. Okay. So basically for the generalization, it's usually total because superclass is derived from the subclass. So if you take a look at the one below here, it means that employee may be secretary, maybe technician, maybe engineer or not, because you have single line over here. And you have D that say that if you are a member of subclass, you can only be one of the subclasses only. But on the top example, you have part entity here, and you have the O, it means overlap. So it means that each of the part can be manufactured part, can be purchased part, or can be overlapped, can be both manufactured and purchased, all right? However, the double line there says that any of the part you must choose whether or not it is manufactured or purchased or both, but cannot leave blank. It must belong to subclasses for sure. All right. Okay, so this is the meaning of disjointness, which signified by D and O. The completeness will signify with the double line or single line. Now, so the total, we would have disjoint total, disjoint partial, overlapping total, and overlapping partial. So the combination, 4 combinations there. And there are some insertion and deletion rules there too. If you delete an entity from a superclass, then it implies that, you know, the subclass must be deleted as well. But if you insert an entity in the superclass, you imply that the entity is mandatorily inserted into all predicate defined. If you have a predicate defined or attribute defined subclass, for which the entity satisfies the defining predicate, right? But if you inserting an entity in the superclass of a total specialization, total, meaning that it implies that the entity is mandatorily inserted in at least one of the subclasses. So it really depends on how you model it beforehand, right? That you want it to be total or you want it to be partial. So when you delete or you insert, it will naturally take the characteristics of what you model. Okay, so it's the same idea as the of the object oriented. When you inherit the property you inherited from their parents, right? Now, there are some more of the terms here. I don't think I can finish all 10 pages. It's called specialization, generalization, hierarchy, lattices, and shared subclass. Let's begin with the a subclass may itself be further subclass. Okay, may have further subclass specified on it. And whenever you have more subclasses nested or you have more hierarchies, it will be called a hierarchy or a lattice. Okay. Now, if there is a hierarchy, it would have a constraint that every subclass has only one superclass. Okay, you have a single inheritance when you have a single superclass, right? Imagine like object oriented, you have one superclass and you have subclasses. So whenever the subclasses have one superclass, we'll call it a hierarchy. Now, you have a lattice, which is another thing. When a subclass can be subclass of more than one superclass. So if you belong to many superclass, it's no longer a hierarchy. We call it a lattice. All right. But in either one, whether a lattice or hierarchy, the subclass inherits attribute not only of its direct superclass, but also of its predecessor superclasses. If it becomes like nested or in many hierarchy, it would inherit the attributes from the top, from everyone above it. All right. Let's take a look at the example here. So with this, a subclass with more than one superclass now is called shared subclass. Okay, let's see the example here. The example here would show a specialization lattice with shared subclass. All right, what does it mean? If you take a look at the engineering manager, let's say that engineering manager is a subclass of an engineer, also a subclass of manager, a subclass of salaried employee. So it has many of the superclass. So it is a lattice, not a hierarchy for sure. Now, it is a shared subclass of what? because a subclass with more than one superclass is also a shared subclass. It's subclass that belongs to, it's a share because it is shared by many of the superclass. See, so employee also have engineer as subclass. Engineer have engineering manager as subclass. Salary employee has engineering manager as subclass. So this engineering manager by itself is also a shared subclass. So now you can have specialization hierarchy or lattices or generalization hierarchy or lattices. It means that it's just a reverse process. It's specialization or generalization. It doesn't, what I'm saying here on the second line, it doesn't matter whether or not whether it is a specialization or generalization process. If the hierarchy and lattice can appear from any process, right? But if you do specialization, you always start with the entity type and define subclasses, right? But if you do also in generalization, you start with the entity types and then you group them into common ones. Okay. And usually it's a combination of the two can be employed. So here is a specialization lattice with multiple inheritance for a university database. Take a look at the student assistant here. You have student assistant who is an employee and also a student, right? An employee and a student belongs to person superclass. So student assistant here will take the attribute. It will also inherit attribute from every superclass that comes before it, right? And now student assistant also have subclasses called research assistant and teaching assistant. So if you take a look at this here, you can see a lattice. When you see a lattice, it means which is the student assistant. It has several superclass like this one here. All right. I have 3 minutes. How far I can go? uh, let me let me finish this union type. So another thing is called categories or union type is the same thing. So what it means is that okay. Wait. Okay. The meaning is that all of the superclass or subclass relationship have the that we have talked about so far is a single superclass, right? Have single superclass unless it is a shared subclass, which is a subclass in more than one distinct superclass, right? But it still has single superclass on top, right? It ends up with single superclass with multiple inheritance. But in some cases, you need to model a different one with the relationship with more than one superclass, all right? And this one is called a category or union type. Take a look at the diagram here. You have a car, right? Car is underneath car or truck, and we call it registered vehicle. However, here is one that I want you to look at. You owns a vehicle, right? You own a vehicle. You are an owner of vehicle. However, an owner of vehicle can be a person, can be a bank, or can be a company, right? Now, person, a bank, company all have different attributes because they do not have the same characteristics. So here, what we say is that when you are an owner of a vehicle, it can be any of this. So you can union it. The words union type come from this. It means that an owner can be a union of person, bank, or company. So when an owner is a bank, then the person and company may be null. So when you union it, you just see that bank is the owner of that car. Or if it's a person, then you take in this information or these, you keep these attributes. So the set of attributes are all different. That is why you cannot model it such that it comes from the same superclass because the class are all different. You cannot have the same attribute. And in that sense, you can only model it as categories or union types. All right. Also, same as the one below, car and truck can be union to become registered vehicle as well. Okay. So, oh, it's 12 o'clock already. So, yep, I'll leave it here. Then I'll follow with this next week. I only have 5, actually just 4 slides left, which is not much. Oh, let me let me finish it. It's only a little bit. Let me skip this. This is just another example. You can take a look at how they all mess up in here. And here is the notation I use in this slide. Mostly we'll call this Chen notation, but you probably saw the rest used in somewhere else, which is actually the same. And the one that you probably see would be Krauss-Foot notation. You won't see much in this class, but if you see something like this with other ER diagram, like when you're working on internship or something, you probably see this. It means the same thing, all right? Or you probably see UML. But now you'll be using a database design tool to draw all these diagrams. And the one that I recommend are the one that I circle here. These three are the one that I recommend that are easy to use. And that's it. Yay. Finally. Yay, finally. Thank you so much. Oh, by the way, please join Discord and then discuss the group project members in Discord because I most of the students already have groups for the projects, and then we'd like to invite the exchange students to join each of the group. Okay, maybe like 2 in one group, 2 in another group, things like that. All right, so we can discuss that in Discord. All right, see you next Tuesday.